So let's say we have an Ethernet network here, and there are 4 computers here connected to a switch. And so each of these computers has a MAC address, and any of the computers can send frames to any of the other computers just by addressing it to the appropriate MAC address. Now we also talked about point-to-point links. So here, each of these computers can send frames over these PPP links to whatever they're directly connected to. So for example, this device here in San Francisco can send frames to Seattle or to Denver, but it can't send frames to New York because it doesn't have a direct PPP link to New York. So what if we do want to actually send information from San Francisco to New York? Is there some way we can forward that information through Denver here and have it pass it along? And what if we actually want to, let's say, connect our Ethernet network over here in San Francisco to this device? And let's say we have another Ethernet network over in New York over here, and we want to connect that as well over here. So the interesting question now is like, how do we send information from a computer on this Ethernet segment here in San Francisco to another computer all the way over here on this Ethernet over here in New York? So to help us explore this a little bit more, I've redrawn this scenario down here in a little bit more detail. So we've got our Ethernet network over here on the left, and this is a multi-point link here. So I've shown all the computers connected, to this vertical line just to kind of show that any of them can send frames to any of the other ones that are connected to this network. Then we have the other Ethernet network over here on the right, and what we want to do is be able to send a frame from this computer over here. Let's call it host A. To this other computer over here on the right, which we'll call host B. Now, both of these computers are using Ethernet. So one question you might want to ask is, what happens if this computer over here, host A, just sends a frame with host B's MAC address as the destination? Well, what would happen is that frame would get sent on this Ethernet, but none of the devices connected to this Ethernet here, none of these devices have host B's MAC address. So none of these other devices have that MAC address. So all of them are just going to ignore that frame if host A sends an Ethernet frame with the destination of B, because it's not going to go beyond this Ethernet. So is there some way to get this device here, this device in San Francisco, to forward that frame over the PPP link? Well, if we just did that, then we'd actually run into another problem, because remember, PPP doesn't use MAC addresses the way that Ethernet does. So when this frame got to Denver, then it wouldn't have that destination MAC address in it anymore, because that was only on this Ethernet. So if we just take that frame, stick it into PPP, PPP doesn't have the destination MAC address. So Denver gets it, and Denver's not going to know what the destination is. So Denver's not going to have any idea what to do with the frame. So what we need is some other type of address that isn't specific to Ethernet or isn't specific to PPP that we can use across this entire network. So if host B has some sort of universal address that's understood everywhere, then all of these devices in the middle, these routers in the middle here, would be able to use that address to forward data to the right place. And so the address that we use is called an IP address, or Internet Protocol address. Internet Protocol, or IP address. And the word internet literally means inter, or between networks. And so the Internet Protocol and IP addresses are exactly what we would use to send information between networks, which is what we're trying to do from this network to this network. And so what these IP routers do is they're connected to multiple networks, and there's some frames arriving here, let's say on interface 1 of this San Francisco router. And inside those frames is a packet of data with a destination IP address. And so the router's job is to look at that destination address and decide whether the packet should be forwarded out this interface or this interface. And so if it decides to forward the packet out interface 3, let's say, then it will encapsulate that IP packet inside a PPP frame then and send it on to the next router over here. And then the Denver router will do the same thing. It'll look at the packet inside the PPP frame, look at the destination IP address, and decide which of these interfaces it's going to forward it out of. So that's what routers do. They receive packets on each of their interfaces and make a decision about which other interface to forward them out of. And so that's the process of forwarding. And so for that to work, each router needs to have what's called a forwarding table that tells it how to get to each destination. So for example, this router in San Francisco needs to somehow learn that to get to the IP address for this host over here in New York, it should forward the packets out interface 3 and not interface 2 or somewhere else. And so the process of building that table is called routing. The process of actually using the table to forward packets is called forwarding. So the addresses we normally use for IP are 32 bits long, and there's also IP version 6, which uses 128-bit addresses, but the internet is still predominantly using version 4, which uses the 32-bit addresses. So with 32 bits, that means there's about 2 to the 32nd possible addresses, which is about 4 billion possible addresses. And so you might imagine that each of these routers have a forwarding table with up to 4 billion entries, one for each IP address, saying, to get to this address, go out this interface or go out that interface. And in principle, we could do that, but 4 billion entries is in the forwarding table that we'd have to look through for every packet that's forwarded is an awful lot. So what we can do is, instead of listing every address individually, we can group ranges of addresses together by prefix. So maybe the IP address of this computer over here in New York is, say, 172.17.6.2. So Denver, for example, could have a route in its forwarding table that says to get to the prefix 172.17/16, and I'll explain what that is in a moment, go out interface 2. And so when Denver receives a packet with the destination of this 172.17.6.2, it doesn't have to have that exact address in its forwarding table. It can just match this prefix. And so this slash notation here, this /16, tells us the prefix length. So the 16 after the slash means that this route here, this 172.17, matches the first 16 bits of the address. So if the router receives an address of the 172.17.6.2, or a packet with that as a destination, the router will be comparing this in binary. So what this is in binary, the 172 is, let's see, 10101100, that's 172, and then 17 is going to be 0001, 0001. The 6 is 00000. I'm running out of room. Let me just move this over, make myself a little bit more room. Oops, there we go. And so 6 is 0110, and 2 is 000010. Sorry, that doesn't quite fit. But so this is 172.17.6.2 here in binary. So since the prefix length is 16, that means that this prefix, this 172.17, will only be compared against the first 16 bits of this address, which is just up to here. So this is the first 16 bits, which is just the 172.17 part. And so we can just kind of ignore the 6.2, the last 16 bits of the address. So we can just ignore the rest of the address because this prefix matches the first part, and that's enough to know that we should forward out interface 2. So we should forward that packet that way. Now, in reality, this forwarding table will probably have a bunch of different entries. So maybe we also have an entry for 172.20/16, which says go out interface 1. Or maybe we also have a route for 172.17.6/24, which says go out interface 3. And maybe another route that says 172.17.8/24, go out interface 3 as well, and so forth. So maybe there's some more entries here. And so now what it does when it's looking up destinations in this table is it picks the longest matching prefix. And so for this 172.17.6.2, both of these entries match, right? 172.17 matches, as well as 172.17.6 also matches. And so because it matches both of these, what it'll end up doing is it'll end up choosing this one here because this is the longer match. It's 24 bits instead of 16. And so in this scenario, the packet would actually get forwarded out interface 3. So it would get forwarded down here to Atlanta, which, presumably Atlanta maybe has a route that takes it on to New York.